Okay, so the first one is 10 microfarad connected to 100 volt supply. Calculate the charge on the capacitor and energy stored. Oh, so I calculate wrongly. I calculate the energy stored first, CV square. So this one, 10 microfarad convert to SI unit. There's your half there. And then 100, you square that, get 0.05 joule. Sorry, I did not calculate the charge stored. First thing is calculate the charge stored. Okay, charge store is Q equals to so the charge store you should be able to calculate yourself, isn't it?
Yeah, sure.
So I don't think I will do that. It's just Q equals CV. Okay, let's go to part B then. Charge store, you just use Q times CV, that's all. Then energy supplied, you should be able to calculate that. That's straightforward. Become more challenging. The charge capacitor is...
So Q equals to CV is 10 times 100, right?
You have to convert it to... Okay, we are not sure, we can work it out.
Yeah, CV square lah, sir. This is CV what?
You go CV only, if you want to calculate charge. Yeah.
Just take the 1.0 times 10 to the power 86 times 100.
Times 100, that's all. That's all. Just equal times that, 10 times 100. Okay, times 100. So it's 1.0 millicoulomb. That's all. Okay with that?
Yeah, okay.
Second part is a bit more difficult. The capacitor is disconnected from the supply and a 5 microfarad capacitor. This is a 5 microfarad capacitor, which is initially uncharged, is connected in parallel across it. Calculate the final potential difference across the capacitor and the total energy stored in both capacitors. Explain any changes in energy stored. Okay, so that is the initial part, 100 volt. Calculate the final potential. So important to realize is that the negative charge, this one got potential, this one got no potential. So the negative charge will try to discharge. So you will accumulate here negative charge, and positive charge will accumulate. So they keep on moving, or current will flow.
Same potential difference.
Until the potential difference is the same. Yeah, you are right. The charge will flow until potential difference is the same. Then we just use conservation of charge using this formula to calculate charges. So total charge initially equals to total charge finally. So total charge initially we have calculated here. And total charge finally, I'm taking it out, 10 plus 5, right? 10 plus 5. And remember, I'm using microcoulomb because it will cancel off anyway. If you are particular about SI unit, you can convert to SI unit. Right? I'm using microcoulomb here. Microcoulomb here, initially was 100 times your V. I calculate out, I get 66.7. Okay with that?
Oh, the finally one is champo lah, cher.
I just take it out, common factor. Because 10 times is basically 10 times V, 5 times V. So it's basically parallel if you like.
Okay. Cher, B, right, teacher, the question.
Yeah.
So basically what is it's trying to tell that because there is no like battery supply or anything, that means there's one charge capacitor already, so that means it will memang flow, and then the other one is uncharged. So with the charge capacitors help, what's that potential difference will keep on flowing until it becomes the same. That's what I'm trying to tell, right? Sure.
Yes, the charge capacitor will keep on discharging until both of them have the same
Okay,
potential. Then the current will stop flowing.
because it's giving supply to the 5 mu f capacitor also,
Yes.
right? Because it doesn't have a supply.
It doesn't have a supply, it got nothing, no charge there. So the charge all come from a 10 microfarad capacitor because that one is charged up. So it has nothing there.
Okay.
It will charge, the charge will keep on flowing until both of them the same potential. That's why we are using same potential. And then the charge store initially go to charge store finally, it cannot disappear. Right? Whatever is initial must be the same as what is in finally. So that's what we are using. So I'm using 10,
Okay.
10, right, which is my Q, which is my C, and then V is 100 initially. I'm using micro. Doesn't matter because it will cancel off. As I say, a particular, you can convert to SI unit. Right? Because your whatever that value for V, you will get your value for V back. If you put that 100 volt, then this will be in volt.
Yeah, even though mu f or even f also
Yeah,
they don't,
because the V will
circle the
cancel
these
off.
values the same.
Then energy stored, right? Same formula, except now you use the resultant capacitance.
102 CV square.
Right? These two add together is 15. Convert it. This one you must convert already because you want to use SI unit. And then that is the potential. Then you get that. So energy is lost in the wire, the difference.
Okay, go back again. Okay. Oh, now I can understand the topic now.
We've done that already yesterday.
Yeah, I was concentrating that.
So energy
What happened?
is dissipated in the wire in the charging.
The half.
Not half. Is it half?
No, they didn't say.
No,
But
it's not half. It's not half.
the lesson that day, the half thing.
Half is if it's from power supply itself.
Okay.
Not half I can see this is already lost from the power supply already. So this one is
Yeah, correct.
right? Only for the direct power supply. Energy is dissipated in the wire in the charging of your 5 microfarad. That's all. The charge has to flow in the wire. Any comment? Anything still not clear?
Now I can understand it now.
The only way to force it in is to try the question already. So you should be able to, after today, try the multiple choice already. Focus question. Okay, you have completed that. Anything else?
Number 4.
Okay. Capacitor C1, there's a C1 of capacitance 4 is charged until the charge in it is 400 microcoulomb.
So we know the volt is 100 lah.
Another capacitor C2 of capacitance 5 is charged until it's 230 microfarad. The two capacitors are then connected as shown. So positive, positive, right? So they are charged differently. So it means they will have different potential. Calculate the potential difference across the capacitor and the total loss of energy.
Okay, let me try. The C1 right is 400 divide 4, you get 100. The other one is 230 divide 5, you get 60, 40, 46. Is it correct?
Conservation of charge first, and the potential must be the same. The charge will flow until the PD across each of the is the same. Then you use your Q equals CV to calculate the initial charge equals the final charge. So initial one, right? Initial one is 400 plus
Oh yeah, this is a
230.
series. This is a series diagram.
Yeah. I think I've done something wrong here. Oh, correct. This is the charge. Yeah, there's the charge initially. Charge finally. Right? Charge finally is just C times V. C is 4 times 5. I'm basically using microfarad. That's why I didn't convert it. I'm using the same microfarad here. 4 plus 5. 4 plus 5. Final potential is V.
Yeah, still can watch.
Yeah. Then I get my answer. Then I need to calculate my initial energy. Total energy initially
is 70.
right? You have to, I'm using Q square C, right? Q square C, because you are given Q and C.
Oh.
That's your Q. When you calculate value, energy, then you have converted.
That means you use from the V equals to Q over C lah. That means
this is Q, right? Square that, change to SI unit. Q square C is this one, convert to SI unit, right? There's a half there. Then same for the other one, half. There's your Q, convert to SI unit, square that, by 5. That one there, 5. Then just use calculator. And after that, calculate the right, that's the initial one. Right, final one, look at the Q. Right, final Q is still the same. You just add the two together. Right, the final charge is still the same. It cannot disappear. That's the final charge. And 10 to the power minus 6, convert it to SI unit, Q square.
so you plus it lah. Minus, they say total loss.
And then your final capacitance is you just add the capacitor together, 5 plus 4, and 10 to the power minus 6 as well. Can? Then you subtract to find the loss in energy.
Empty.
Oh, what am I doing? Joe. Okay, I will carry on with our new discharging and charging.
Mm.
The others you can ask next week.
Okay.
You should digest it and then try to do yourself, learn yourself.
Mm. Okay.
Okay, remember your
Integration.
integration, adding of log, right? When you subtract, that's how you take the division. Or if you add, you multiply, that's how you do that.
Mm.
You integrate that. You got integrate 1 over x, you get ln x, or 5 over 2x, you get 5 over 2 ln x. So remember that. That's your maths problem. So yesterday, we start off with integration, right? We start off with a charging capacitor. We close the switch, the charge will flow. Right? As I said, you have to learn to accept that. Sometimes I will use electrons, sometimes I use positive charge. Positive charge is just an imaginary charge as well. Positive charge will flow, and then here become positive, and then positive charge will flow there. That's called conventional current.
Sorry, sir. Repeat again, sir.
The positive charge from the positive terminal will flow.
Okay. Okay.
Charge up the positive there. Positive will repel
Okay.
from the lower plate and then goes back to the negative terminal. So it means that the
Okay.
potential across the capacitor will start increasing.
Okay.
So that's what we did. Right? Initial current we can calculate from here because the initial voltage is this one. So E divided by R, that's the initial current flowing. Right? So the voltage will keep on increasing until you reach the final value. Right? You cannot go further than what is given. That is what is given, E. Then we integrate and show you how to get the formula. Integration
Integration.
more complicated lah, this one. Yeah, this is the one more complicated. So that one you go back and review yourself. So that's what we get.
Okay.
That's the graph.
Mm.
Right? And then we introduce the idea of this one Greek alphabet tau. We call it time constant, RC. We will introduce that, we will define that properly later. So now we are looking at charge. Yeah, it's just the same thing. Q equals CV. C is constant. Right? So charge, the same thing. As your V increases, your charge will increase because it's the charge that
Correct.
the potential. So we use our
Directly proportionate.
place that into here. Right? CE, remember there is the initial charge Q naught. Right? Q naught equals to CE. Right? We're just using this one, this formula. Initially is the V becomes your E. That's the initial voltage.
Huh? Not CV, sir.
We use E one. That's our battery, EMF of the battery. Your book use V naught, it's okay. It's just a choice of symbol, that's all. V naught is your final
Okay.
voltage, that's all. So you should be able to draw that. This is U naught. That's your time. That's your charge. So it's the same. The graph is the same as your
This one
voltage.
memorize can, right?
Memorize. You have to memorize the graph or know how to sketch the graph.
Okay.
Right? Charging, the potential will go up across the capacitor. The charge of the capacitor will start increasing. So that's how to remember.
Mm.
Current flow is a bit easier. Right? There's your voltage across the capacitor. Current is dq dt. Q equals CV. Right? You just differentiate the Q. Then you get C dV dt. Then you just differentiate that. Right? Differentiate that. The constant disappear. This negative and this negative will come together, become positive. and then you still got your differential there. And remember that E over R is your initial current. Just replace that. And that's how the graph looks like. Remember, it doesn't go to zero. Go to zero at infinity. This one is got for internet, poorly drawn. So it's poorly drawn. Now that this one is I naught. Okay. Only goes to zero at infinity. So this one is poorly drawn. Okay, so there's a three type of graph that you need to know. How the voltage build up, how the charge build up, how does the current decreases. Then what next part is note, right? Sometimes instead of writing this one becomes a bit too troublesome, especially we use PowerPoint. Then usually we prefer to write this way, exponential. It's the same, just a bit.
Yeah, I know how to write exponential.
Right now we define time constant. Basically, is
So the CR.
ERC is the time taken for the current in the circuit to drop to 1 over E, which is about 1/3 lah, or 37% of its initial value. Now, we are not particular. Usually it's about 1 over 2.7 something. So we take it to 1/3 when we sketch. Right? That's what we do. We put our RC, we put our tau into here. Then this become e to the power minus 1. So I naught e over 1 over e. That's how we get the value, 37%. Okay, so that's how the graph looks like. This is your I naught. There's your infinity goes to 0. So time constant, normally that's how we sketch the graph. We have a time constant, and then that is your 0.37, or we just about estimated about 1/3. Right? Sketching, we don't have to be very particular. As long as it's about 1/3, good enough. Right? That's your VT graph. So VT graph, the same RC, means it will have to, if this is decreased by 1/3, this must increase by 2/3, 63%.
Opposite lah.
Opposite, that's all. About lah, don't need to be particular because we are sketching. Not worry about the exact value. Just roughly how the graph looks like.
Memorize.
Okay with that?
Okay.
Right? The idea of the term RC is a resistance of the resistor multiplied by capacitor, and it's known as time constant. So the unit is time, second, if you use SI unit. So if you use voltage, then it should build up to 63% of the final value of the initial final value, right, in 1 RC. So 99% transition for 5 RC. So literally it's almost zero.
How do they know like 1 RC 63 and then 5 RC 99.9?
Calculate out. That's how we calculate out there.
How they calculate?
There. There, here.
Uh-huh.
It's about 37%. 1 over
Yes.
E times 100 is get about 33%.
Okay.
So if 33%, this is 2/3. Right? These two add together must be 100. That's your V. Okay now. You can play around with the formula when you are free. Go and play around with formula. The voltage is 2/3. So by 5 RC, basically the capacitor discharged completely already. Okay, so nothing much about that. Just to tell you roughly when you sketch the graph. Okay, discharging. Page 63 in your book. Discharging, we don't have a source there. Right? Just now we have a battery here. The current will flow clockwise. Now the capacitor is fully charged. We short circuit it. So now the current is flowing flowing anti-clockwise now. Anti-clockwise. Right? Suppose the PD across the capacitor is E initially, and the charge is Q naught, right? Where we started just now. At time 0, the voltage is E or V naught. So the charge is CV, right? V initially is E, that's why we use that. So that's where the current will flow. So when the switch is closed, same thing. I know it's E over R. This capacitor now become like a battery, discharging it. So the potential is E initially divided by R. That's how we calculate the current through the resistor. Current is flowing anti-clockwise, flowing from the capacitor.
Sure, go back again. Okay, the discharging, that means
It's going that way. Previously, it's coming this way.
oh, opposite lah. Oh, discharging. That means charging means it comes from negative, and then the discharging comes from positive lah.
You just have to
Right, sure.
learn to use conventional current. Right? Charging is coming from here, the battery. So it's going clockwise.
Yes. So it's just
Discharging,
opposite only lah.
going opposite direction, anti-clockwise.
And it's coming from the capacitor itself.
Yes, the capacitor now becomes a battery. Except that it's not
Okay.
constant source as well. So initially,
Except there's no what?
except that it's not a constant supply. It's the
Okay.
charge
Okay.
decreases, the potential will decrease. So initially it's E. As a capacitor discharge, the PD across the capacitor decreases. That's what I mean. Right? It depends on the charge here. It's not a battery. Battery is a constant power supply, constant voltage supply. Capacitor, no, it depends on the charge there. If there is charge there, it has a potential. If the charge decreases, the potential decreases also. So that's how we calculate our voltage equals to IR. Right? I we can calculate from here. So anytime we can calculate the voltage across R, which is the same as across C. And Q equals CV again. I is, we put a negative sign to show that it's a negative, the other direction, different from previously, dq dt. And then we replace the Q with that. So you get minus C dV dt. And our V equals to IR. I, we have got this is your I. Right? Replace the I here, we got RC dV dt. Discharging is easier, right? Less complicated. Then we just take our dt across there. We replace our I. So now we take our dt across, take the v down. That's why we get negative times u there.
This one I have to play formula around lah.
Yep. Then we integrate that. Right? This one is more straightforward. Okay. Like that. Let's take anti-lock. So our E take across there, that's how we get that. And then instead of RC, we replace it with tau. So we can see that V decreases with time.
Yeah, the anti-log it and make it e to the power of negative t over
Always remember,
RC.
when you discharge, the charge on the capacitor decreases, so it means the voltage on the capacitor will start decreases. Then you can remember the formula. So
Again,
that's
sir?
the graph will look like. Right? As the charge on the capacitor decreases, the voltage on the capacitor will also decrease.
Charge decrease, voltage also decrease. Okay.
Right? Voltage decreases with time. So we want to know the charge, same thing as we just say. V decreases, the charge also decreases, because it's the charge on the plate that determines the potential across the capacitor. So we just place our E there with our V there, place it inside here, CE. So CE becomes Q naught. Right? So the charge of Q and V is the same. To catch, we just use your time constant. It's about 1/3, right? Roughly about 1/3 there. Okay.
You should have no 1/3 again, huh?
Say again.
How you know it's 1/3, huh?
It's the same idea. We are using 1 over Q naught over E. E is about 2.7, so it's about 1/3.
Oh, okay.
Sketching, we don't have to be precise. We just roughly estimate 1/3 good enough. Slightly more
That
than
means like 1 over E lah.
yeah.
Okay.
Current, same thing. Right? V decreases, current also decreases. So our current is the same. Go to our definition. We put a negative sign there because it's different direction, dq dt. And then the value of Q, put inside there, differentiate that. That's what we get. Right? E is Q naught over C. Q naught over C is E. E over R is I naught. Okay.
Wait, answer. Q naught over RC and then I wanted to ask like, oh, that means you substitute E equals to RC lah, that means.
Yeah. E equals to Q naught over C. And then Q naught over C is E. That's how we get our ER. Huh?
Oh,
ER.
you just times 1 over R lah.
E over R is I naught. That's all. So this is I naught.
No. Because the note, right, so the R you just times 1 over R, what basically, right?
Huh? What do you mean times 1 over R?
No,
Then
because if you look right, so E equals to
E over
Q.
R is I naught. E over R is I naught.
Oh, I not. No, but where did the R came from? That's what I'm asking.
R from here. From the differentiation.
Oh,
From the differentiation here. RC
okay.
negative and negative cancel off.
Okay.
Okay, so that's how the graph will look like. Okay, we have to stop now.
Okay.
So 5 minutes break.